King's Doctoral College, and I'll be co-hosting today's event.
My name is Lina Nadaro, and I'm the Doctor of College Development Associate within King's Doctoral College, and I'm also your host for today's environment.
I've had the privilege over the past couple of months of organising this year's competition and seeing how much our finalists have developed and improved their presentations along the way. It's been great to see. 3-Minute Thesis is a competition that happens at institutions across the world, and it challenges doctoral students to communicate the complexities and the detail of their research in a clear, concise, and accessible way, in a way that us, a non-specialist audience, can understand. Our doctoral students, our finalists, have challenged themselves to take what would ordinarily be summarized in tens of thousands of words, accompanied by many a figure, photo, line of code, quote from historical text, and much more, and summarize it to us in just 3 minutes.
I must say, it's really impressive the work that goes into it. I personally had the privilege of being a semi-finalist judge, and being that opportunity to look at the semi-finalists and review the work, their effort, their ideas and creativity as a semi-finalist in just and they presented it in just 3 minutes was very impressive. So I really commend the finalists for getting this far. It's not a small feat, and I think it's an achievement in its own right. And so how will the 3MT Grand Final work? So our finalists are tasked with presenting their thesis in just 3 minutes. So they have to present using a single static PowerPoint slide and using only spoken words. And our judging panel will be judging based on 3 criteria. So the first is substance. That is what they say and the content of their talk. The second is engagement, professionalism, and enthusiasm. That is how they deliver their talk. And then finally, the PowerPoint and how well our presenters use this PowerPoint to enhance or complement their research. So without further ado, I would introduce our wonderful judging panel. So first, we have Bert Gallimore, who is the King's 3MT overall winner in 2024, a doctoral researcher within the Institute of Psychiatry, Psychology, and Neuroscience. Next, we have Lizzie Ellin, the Senior Communications Manager within the Faculty of Natural, Mathematical, and Engineering Sciences. Next, we have Tanya Graham, the Innovation Skills Executive within the Translational Research Office. And next, we have Nigel Eady, the Director of Research Talent within King's Doctoral College. And last but not the least, we have Emma Tallam, the Entrepreneurial Skills Manager and within the King's Entrepreneurship Institute.
From our 9 finalists, they're going to confer and decide upon their Judge's Choice winner and runner-up, and they're going to be winning some cash prizes. Our overall Judge's Choice winner will then go on to represent King's at the national competition later on in the year. And you, our audience, both online and in person, will get an opportunity to vote for your favourite, your People's Choice Award winner. So do pay attention, think about which presentations spark your interest and inspire you, leaving you wanting to know more. I think that's it from Lillian and I. You've heard enough from us, so I'm going to invite our first speaker, Rosie, up to the stage.
Thank you very much.
Is that working okay?
Yes.
Yeah, okay.
So yes. So first up, we've got Rosie Barrows from the School of Biomedical Engineering and Imaging Sciences with their presentation, Cardiac Digital Twins, From Code to Care.
As in, are you going to change the slide when I start talking? Is that the plan? Sorry. Just I did spend a while working on it. Cool. Okay. Let's say I've designed a new car. It looks great, but how do I know if it's safe? If I crash, will it protect me? We don't just hope for the best when we're designing new cars. We use crash test dummies to simulate accidents. And my research uses that idea, but applies it to medicine. So when we're developing new drugs, we often rely on animals like rats or pigs. And some drugs work brilliantly in rats, but they're dangerous or ineffective when we use them in humans. So what if we could try it in a human first, but without any of the risk? That's where my work comes in. I'm creating a computational model of a patient's heart, a cardiac digital twin. It starts with a scan of the chest to map the size and shape of the heart. Then, inside the computer, we create a mesh with millions of tiny elements. And by incorporating details like the direction of muscle fibers, we can solve equations to simulate how electricity flows around the heart and how it contracts. Now, the really tricky part comes with fine-tuning these models so they behave just like a real patient's heart. Do they reach the right blood pressure? Do they contract quickly enough? Do they eject enough blood? Our models have hundreds of interacting parameters. And every time I want to run a new simulation, that takes 5 hours of time on the national supercomputer. In terms of energy, that's like boiling 100 kettles or driving 70 kilometers in a Tesla. With that kind of energy consumption, we can't just keep running and running simulations until we find the right combination of parameters. So we're using AI to predict how each tiny cell property influences the heart's performance, which helps personalize the models. Once we've got our cardiac digital twins, the possibilities are endless. That dream we had earlier of a crash test dummy for the heart is now a reality. For example, I've been testing a drug called amiodarone. You can see it on the right-hand panel here. We give patients amiodarone when their heart has slipped out of its normal rhythm, a condition we call atrial fibrillation. And although amiodarone works really well at fixing that abnormal rhythm, our models predict it might actually weaken the heart's ability to contract effectively, reducing how much blood it can pump. And that's really important for patients with heart failure, where the heart's already struggling to meet the demands of the body. With insights like this, doctors can make safer and more personalized decisions for their patients. And this is just the beginning. We're exploring how to predict the outcomes of surgeries and investigating how your hormones might increase your chance of developing an arrhythmia like atrial fibrillation. Thanks to this fusion of imaging, modeling, and AI, we're replacing hoping for the best with precision and confidence. We're shaping a future where personalized medicine is the norm, with our models sitting at the heart of clinical decision-making. Thank you.
Thank you very much, Rosie. That was absolutely brilliant. Next, we have Kaat De Backer from the School of Life course and Population Sciences with their presentation, Infant Removal at Birth, Insights from Healthcare Records and Unheard Voices.
Did you know midwife means with woman? It's our job to make sure both mother and baby are safe and well cared for. But the first time I witnessed a baby being taken into foster care while the mother was still recovering on the postnatal ward, I didn't know how to be with woman. Like the midwife here in the middle, I was confused and I didn't know how best to support her. How often does this happen? Well, in 2023, almost 7,000 babies were already known to children's social care before they were even born. And in the same year, nearly 5,000 infants under the age of 1 went into care. Children's social care becomes involved because they're worried about these babies, but we should also be worried about their mothers. Many of them find themselves on unsteady ground because of a difficult childhood or current challenges such as poverty, poor mental health, domestic abuse, or substance and alcohol use. Add the trauma of having your baby taken away from you, and you can see these women may fall between the cracks. So what should good maternity care for these mothers look like? Well, my PhD uses 3 different approaches to answer that question, guided by an advisory panel of women with lived experience at every step of the way. First, I analysed healthcare records of pregnant people in South London. I noticed that those under the age of 25, living in poverty, of black or mixed ethnic backgrounds, and those with previous contact with mental health or social services were more likely to have children's social care involvement. Second, I interviewed women who had a baby removed. They told me pregnancy was an uncertain time and children's social care assessments loomed over them like a dark cloud. The separation from their infant left a gaping hole, as you can see here, and they were often left to deal with that trauma on their own. What they wanted was kindness and support to tackle the challenges that led to the separation in the first place. 3, I investigated UK data of all women who died during pregnancy or the year after birth and who had a baby removed or had involvement with social care. We found that these women had often very complex medical pregnancies, and the combination of medical and social risk led to a wave of professionals becoming involved. It made the antenatal appointment schedules confusing and overwhelming. Professionals didn't always work together, and women were often judged. My research matters because it provides the evidence to rethink care pathways for this group of marginalised mothers, and to make sure their care is trauma-informed, joined up and easy to access. So if my PhD can make that cloud a little bit less frightening, it's the biggest reward as a midwife and researcher. Thank you.
So next up, we've got Tiffany. So yes, our next finalist is Tiffany Baptiste from the School of Biomedical Engineering and Imaging Sciences with their presentation, The Heart's Hidden Springs, a new way to treat atrial fibrillation.
Picture this. It's a bright summer's day and you've just set up a new trampoline in your back garden. At first, the fabric flexes easily, bouncing back with every jump. But over time, it stiffens, making it harder to rebound. Now, imagine that trampoline is your heart. When it's healthy, it expands and contracts smoothly. But if atrial fibrillation, or AF, develops, the heart's upper chambers, the atria, stiffen, making it harder to pump blood effectively. AF is a growing health crisis. It affects millions in the UK, increasing their risk of stroke, heart failure, and early onset dementia. Nearly half of AF patients will experience recurrence within a year after treatment. A key reason for this? Fibrosis. That is, tough, fibrous tissue that builds up in the atrial walls, making them stiffer and creating trigger points that keep AF going. Doctors want to target these areas, but how do they find them? Current methods often require inserting instruments into the heart. These procedures carry risks and aren't suitable for everyone. But what if we could identify these problem areas without invasive procedures? My name is Tiffany Baptiste, and in my PhD, I'm developing a non-invasive approach to detect stiff, fibrotic areas of the atria, helping doctors to tailor treatment to individual patients. Let's go back to the trampoline. Imagine watching a video of yourself jumping, but instead of focusing on you, look at the trampoline fabric. The way that it moves can tell us how stiff the trampoline springs are. Now, let's do the same for the heart. Instead of a video, we use CT scans taken in hospital. These images capture how the atria move, and with them, we can build a virtual model of the heart that mimics real-world motion. By fine-tuning this digital model until its motion matches the patient's actual heart movement, we can estimate stiffness across different regions of the atrial wall. For the first time, we can map regional atrial stiffness non-invasively. So far, I've done this in 10 patients. Next, I'll compare my findings to traditional invasive fibrosis maps to confirm that we can successfully pinpoint these crucial AF trigger points. The impact of this research? A new, safer way to diagnose AF trigger points, helping doctors to personalize treatment and avoid ineffective procedures. Just like the springs of a trampoline, the stiffness of the atria influences the heart's motion. By unlocking new insight into the atria's flexibility, my research brings us closer to a future where AF treatment is not just reactive, but truly tailored, helping millions to keep their hearts strong and steady. Thank you.
Thank you very much, Tiffany. That was absolutely brilliant. Next, we have Oliver Roughton from the Department of Languages, Literature and Cultures with their presentation, A Word Can Paint 1,000 Pictures, Ideas of Language in the 18th Century.
What is language? Why do we have it? What's its purpose? These questions have fascinated philosophers and linguists for hundreds of years. And my research focuses on the answers given by these two authors from 18th century Germany, Johann Gottfried Herder and Johann Georg Hamann. I look at how they challenge some of the dominant narratives of their time, and hopefully can still challenge us a bit even 300 years later. But what was so radical about their approach? The dominant view of language, both today and back in the 1700s, saw it as a useful tool for labeling and describing the world around us. Over time, our system of labeling has become more complex and our descriptions more accurate. Sounds like a good thing, right? Yeah, Herder and Hammer weren't so sure. They questioned the underlying assumption that language's ultimate purpose is to label things. Instead, the two Johanns thought that language can paint. That is, it can present an image to the mind in the way a painting does to the eyes. Language becomes the paintbrush of the soul, the medium for expressing human experience in a way which allows us to see each other's perspectives and feel each other's emotions. So, how does this work? Have you ever read a poem and thought, but what does it mean? That question assumes a labeling approach to language, that the words exist to point to things, and the flowery language of poetry is either a nice way to dress those ideas up, or a slightly annoying hindrance to understanding. If we think about language the way Herder and Hamann did, the question makes no sense. The use of things like rhyme, meter, melody, imagery, it's not just a nice way to dress up an idea. It's to paint the images, sensations, and emotions experienced by the author. It's a way for us to see and hear through someone else's eyes and ears. So why does this matter? It's undeniable that no two individuals experience the world in the same way. We're limited by our physical body, shaped by our culture and personal history. To think of language as simply labeling things ignores these unique and varied perspectives of human reality. The constant striving to make language more accurate and pure, reforming things like spelling and slang, asking only what words mean, only which labels apply, removes our ability to paint these perspectives in words. Although my research is ultimately agnostic about exactly how correct they were, it seeks to shine a light on Herder and Hamann's striking suggestion that understanding the world is not a question of applying the most accurate labels, but painting the broadest range of perspectives. Language as art, as the paintbrush of the soul, is not just a fluffy thing to make us feel nice. It's the only way we can truly express our own realities to each other. It's the only way we can grasp human reality in its entirety. Thank you.
Fantastic. Well done, Oliver. So next up, we've got Amalia Miranda from the School of Cancer and Pharmaceutical Sciences with their presentation, The Right Fit, How Disease Models Shape the Future of Tuberculosis Research.
Have you ever bought clothes that looked amazing on a model, but didn't look the same when you wore them? It is very disappointing, isn't it? Now, imagine you are a scientist. You have developed a new medicine and test it on your disease model. But then, when the patient uses it, it doesn't behave the same. It is very, very disappointing. Using irrelevant model for studying disease or testing new drugs is not only cost billions of money, but can also delay life-saving treatments. For emerging disease like tuberculosis, getting it right is really important. Tuberculosis is an infectious disease caused by Mycobacterium tuberculosis, which typically affects the lung. In 2023, this has been caused about 1.25 million of global deaths, making it the deadliest infectious disease caused by a single infectious agent. As a scientist, I've been in the lab creating an accurate model for tuberculosis, but not one that is going to disappoint you. Modeling a structure called granuloma is the best way to achieve this goal. Granuloma exists in TB-infected patients as cluster of immune cells that tries to block the infections. At first, it sounds like a good thing to prevent the spreading of the bacteria, but somehow it can turn into a hiding place where the bacteria can survive and even grow. This structure is one of the reasons why tuberculosis is very hard to eradicate, but this also means granuloma is the best model to be developed. My granuloma model is made in a 3D culture system called spheroid. This system better represents the physical and biochemical environment inside the body. The cells hate being alone, so they need to stick together like friends to communicate and survive. And to make this happen, a multi-layered nanofiber is added and acts as an extracellular matrix. This nanofiber is made from the combination of natural and synthetic polymer, so it's not only providing the structural support, but also maintain the environment and cellular functions. From this approach, it is possible to create a consistent and reliable model for tuberculosis, which accurately represent the disease. So, having medicine that have been tested on the right disease model is like buying clothes that stitch you well and brings you joy. Let's replicate that in science. Creating the right fit through an accurate and representative disease model is the key to a successful drug development, shaping the future of tuberculosis research. Thank you.
Thank you very much, Amalia. That was brilliant. Next, we have Andrea, Mathilde, Ulrichsen from the Department of Psychological Medicine with their presentation, Can Sleep Duration Predict the Ups and Downs of Bipolar Disorder?
Sleep is incredibly important. We all know it influences our everyday life and mood. But what if understanding sleep patterns could be a key to manage chronic mental illness? In my PhD, I set out to investigate just that. Bipolar disorder is a severe mental illness characterized by fluctuations in episodes of mania and depression. Patients experience changes in their moods such as sadness, guilt, shame, and thoughts of death and depression, and euphoria or irritation and mania, as well as changes in their energy, cognition, and the need for sleep. These symptoms go up and down like a roller coaster, and not always in sync, and don't begin at the same time, which can make them feel random and unpredictable. They can also feel confusing. You see the world through a lens of either mania or depression, astronomical confidence, or crippling despair, making it difficult to know what's real. This illness affects about 5% of the population and sadly carries a high risk of premature death, among other reasons due to high suicide rates. Some estimate that up towards 20% of people with bipolar disorder die by suicide. And although there are treatments available, they're not universally helpful and often get more complicated when symptoms get worse, highlighting the need for early intervention. I wanted to see if at-home monitoring of one of the key changes in bipolar disorder, sleep, could help predict onset of mood episode. This would mean a head start and increased awareness of pending symptom burden, which could potentially amend or block development of severe mood swings. My research has two parts. First, a systematic review, and then a data analysis of a year-long bipolar disorder study. The systematic review looked at long-term monitoring of sleep and its correlation with mood changes. And the data collection study asked patients to record their sleep in a smartphone app, and we then looked at the sleep patterns and its correlation with mood episodes. I found that in the systematic review, more sleep was followed the next day by a dip in mood, and less sleep was followed by an increase of manic symptoms. In the data collection study, we found that especially variability, so more fluctuation in sleep duration between days, predicted the onset of depressive episode. These sleep changes could be a key item to know what episode patients are in or about to enter, which could inform them how to best protect themselves, and it can easily be done at home. Bipolar disorder can feel random, unpredictable, and unmanageable. My research will help our understanding of how sleep affects mood, which could give some control back to patients, letting them know what symptoms they're likely to face and then how to best fight them. Thank you.
Fantastic. Well done, Andrea. So next up, we've got Nishat Zakaria from the School of Life Course and Population Sciences with their presentation, Zinc and Copper, the Hidden Regulators of Skin Aging and Disease.
Have you ever looked in the mirror and pulled your skin back just a little bit, telling yourself, no, these aren't fine lines and wrinkles, they're just smart memories? Well, what if I told you that the reason behind these fine lines and wrinkles is just metal? Take a look at my slide. Well, on the left-hand side, we have younger, vibrant-looking skin that is rich in zinc and copper. And on your right-hand side, we have older, wrinkled skin where this metal imbalance can be seen. You see, the issue is, as we age, these metals basically end up declining in a process called inflammaging. This is chronic low-grade inflammation, and this accelerates with skin aging and skin disease. As time passes, zinc becomes trapped, it becomes misplaced. It's basically like your star player that becomes benched at the basketball game. Copper, meanwhile, stays relatively stable within the skin. However, we find that this is really important for wound healing and pigmentation disorders, so it just can't carry the team alone. We need both a combination of zinc and also a combination of copper. So what happens when this balance completely fails? Well, it's absolutely disastrous because skin diseases start to flare up. We have psoriasis, eczema, atopic dermatitis. Wounds heal so much slower. We have hyperpigmentation disorders, all because of these two tiny metals, zinc and copper, completely falls out of balance. So what did I do? Well, during my PhD research, I surgically isolated skin samples from both younger and older individuals in human samples. Then, using a very precise laser, I mapped the elemental distribution of both zinc and copper at the highest ever resolution image to date. What I found was absolutely striking. Zinc doesn't just decline with age, actually it hoards zinc in all the wrong places within the skin. And what does this mean for copper? Well, copper remained absolutely stable, which is fine, but it just can't compensate. The issue is, here we now have an aging-related biomarker for inflammaging, which is the first of the kind in science. Very, very important. So what does this mean for the future? Well, it just means that when you go into the clinic and have a blood test in, you can't have a look at them in solo. You can't look at just zinc and copper. You need to make sure you have an accurate representation of a biomarker within the clinics too, because what stays within the skin actually stays hidden until now. So imagine the future. Imagine skincare-backed science. Imagine your anti-aging creams actually doing its job at a cellular level, fighting oxidative stress and reducing inflammation, targeting inflammation at its root. So your skin just doesn't crave hydration all the time, it craves balance, balance in the right metals. So maybe, just maybe, the fountain of youth isn't water after all, it's zinc. Thank you.
Thank you very much, Nisha. That was brilliant. Next, we have Kirsten Rock from the School of Cancer and Pharmaceutical Sciences with their presentation, Equity in Healthcare, Harm Reduction for People Who Use Drugs.
Let's take a trip to the GP together. Say you get prescribed a new medication. It works great, and you feel better. Or instead of one medication, let's say you get prescribed two. On their own, they each work exactly as intended. So again, you feel better. But if you were to take these medications together, there's side effects that you could experience that wouldn't happen if they were prescribed separately. Your GP would then give you some precautions about when to take each medication so you wouldn't get those side effects. This is a pretty common experience, right? These precautions are in place because when the medicines are being developed, they went through clinical trials that tested their safety and alerted to these interactions. Medicines are also tested against other things, like certain foods or alcohol, and that's why if you read the package insert in a medication box, there can be warnings such as, don't take with alcohol because it can impair functioning. This allows for medicines to be safely prescribed. Over 1/3 of people in the UK have tried an illicit drug in their lifetime, whether it be cannabis, cocaine, or heroin. These drugs, however, are not usually tested against prescribed medicines, so their side effects are not really known. There is also a lot of stigma surrounding drug use, especially for people who are dependent on drugs. This stigma can lead these individuals to delay necessary medical care for their other health problems due to fears of not being listened to or having their concerns minimized as further drug-seeking behavior. However, because people who use drugs likely have poorer health than the general population, it is crucial that their medications are also being safely prescribed. My PhD research aims to improve the healthcare for people who use drugs by identifying harmful drug combinations between prescribed medicines and illicit drugs and create effective strategies to reduce these harms. The key parts of my research can be described with the circle of evidence. The first step is to identify fatal drug interactions by searching a database of drug deaths. The second step is to perform lab experiments to confirm which system in the body the drug interaction is causing harm, like the lungs or the heart. The third step is to monitor these interactions in humans with observational studies. Once all this evidence has been collected, the fourth step is to talk to both healthcare professionals who prescribe medications and people who use drugs who are affected by these drug interactions to help inform the recommendations and optimize the interventions that will be the most effective.
The fifth and final step is to communicate these recommendations to the wider population to promote the safe prescribing of medicines for people who use drugs. With this, the evidence circle is complete. From identifying harmful drug interactions to understanding and characterizing them and working with people who these interactions directly impact, we can make strides in improving the healthcare for people who use drugs. Thank you.
Wonderful. So, last but not least, we've got Mubaraq Yakubu from the School of Biomedical Engineering and Imaging Sciences with their presentation, AI for Pituitary Adenoma Management.
I would like to begin today by asking you a simple question. What would you give if you suddenly lost your sight or half of it? Ponder this question and reminisce on your answer as I share my work with you. Pituitary adenomas are classified as the third most common brain tumors, affecting 1 in 7 people. While they are mostly considered non-cancerous, they can silently grow, pressing on the optic nerve, leading to vision loss. In high-income countries like the UK, early detection through imaging prevents this. However, in low-resource settings like sub-Saharan Africa, late diagnosis means up to 50% of patients face blindness. As a beneficiary of the King's Africa PGR Scholarship, my research aims to bridge this gap using artificial intelligence, or AI, as most of us call it. Using deep learning, I am developing an AI model to automatically detect and measure pituitary adenomas from high-resolution and low-resolution magnetic resonance imaging scans, also known as MRI scans. Early experiments show that AI models trained only on high-quality MRI scans struggle on low-quality scans. However, by incorporating diverse data, performance significantly improved, making diagnosis more reliable across different settings. Our model now outlines the tumor region, the surrounding structures like the optic nerves and carotid arteries, and also provides us with volumetric data, which is crucial for treatment planning and prognosis. This AI-assisted system could transform pituitary adenoma diagnosis, reducing late-stage blindness in underserved regions where radiologists are scarce. Early detection means we can start earlier interventions, achieving better outcomes, which will inadvertently lead to saved vision. We are now validating our performance with expert neuroradiologists and hoping to integrate this AI pipeline into real-world clinical workflows. Now back to my question. What would you give to protect your sight? With AI, we're giving patients a chance to see, to achieve timely treatments, to avoid preventable blindness. AI is not just about data. AI is about vision, literally. Thank you for your audience, and I pray that none of us here today is that unlucky number 7. Thank you.
Thank you so very much. I would like to please invite all the finalists, if you can join me on the stage, please. Massive congratulations to you all. That was absolutely brilliant. And I would like to ask the I was going to ask you all to join me to give them a rousing ovation, but since you've already clapped, let's just give them another round of applause. Thank you, thank you, thank you. Please, you may go back to your seat. Thank you so much. Congratulations to all of you. It was absolutely brilliant. I commend them. Presenting all that in 3 minutes is so brilliant, and I'm so immensely proud of you all, and I celebrate your achievement. So now we would like to invite the audience to vote for the People's Choice Award winner using the QR code on the slide. Yes. So if you scan the QR code, it should take you directly to the voting. There are some steps that you can skip because you don't have to put in your details. You're very much welcome to answer anonymously. But please vote for your People's Choice Award winner. And that's it from us. Congratulations once again to all the finalists. That was very impressive, and well done to all of you. Thank you. Can we zoom out? Let's just go back to their faces.
Well, whilst you're all getting your votes in, I'll take this opportunity to bring the King's 3-minute thesis competition and grand final to a close. Thank you so much for joining us, and congratulations once again to our finalists. You've all done a fantastic job. And thank you to those of you who have managed to join us online. It's great to have you with us. For those of us here in person, we've got a reception outside the lecture theatre, and you're more than welcome to join us there. There's some food and drink if you want to partake in that. We're going to be announcing the Judges' Choice winner and runner-up and your People's Choice Award winner out there, probably in the next 15 or 20 minutes. So do join us if you're able to. Thank you very much, everybody, and I hope you have a lovely rest of your day.